hydrogen atom problem. The electronic state functions for the electron is NLM. There is a radial factor times the angular. This is the radial function, and this one is the angular function. We have defined the radial distribution function as r squared times the radial factor here. This is the radial distribution. Function. All right, let us give some examples about the behavior of this function as a function of r. Notice that all radial functions, radial distribution functions, have zero value at r equals 0 because of this factor, r square here. When r is 0, 0 times anything is 0. And also, at infinity, the radial functions, all radial functions, go to 0 as r goes to infinity, which means r square also becomes 0 at very large distances. And let us note once again that these functions has n minus L minus 1 nodes between 0 and infinity. Such information, such knowledge about these functions make it easy to prepare qualitative graphs of such functions. Let us consider P for 3D, 3S, and make it 3P and 3S orbitals. Let us first graph the R functions. R3S. I'm taking just this factor for the 3S orbital. Now, according to this rule, n is 3, L is, because it's S, 0, 3 minus 1, what is it? 2. It means that this function has one node and another node. let us also note all s orbitals are non-zero at r equals 0. All s orbitals means we have 1s, 2s, 3s, 4s, 5s, infinitely many s orbitals. All of them are non-zero at r equals 0. All the other orbitals other than s are or have or are 0 at r equals 0. So these are the basic knowledge about the general form of these functions. Okay, the R function, the S function, according to this rule, at r equals 0, it is non-zero. So at r equals 0, it has some value like that. It becomes 0 at this point and also that point. All right? So the graph will look like we know that all of the radial functions go to 0 at infinity. So at large distances, it will again turn, and it has such a shape. This is for 3s. All right. Now, the graph means values of the curve below this horizontal line have negative values. Above the horizontal axis, r-axis, values are positive numbers. Okay, now, if you want to graph this, the radial distribution function, we may make use of this graph and think in our mind that, first of all, it is square. Square means any point like here, after squaring, will become a positive number. Also, the radial distribution function contains this r square factor. But this factor, qualitatively, at r equals 0, it will cause this r square times capital R square, to be 0. So qualitatively, it will become 0 here. But squaring the radial function and multiplying with r square, could it change the position of this 0? No, that 0 stays there. Also, this 0 stays there, even when we square it. So what will happen? Then, when we square this, and this part looks qualitatively similar. This is r square times r 3s square. Do you see how we proceed? We first draw the graph of r itself, this function, r function. using such knowledge that it has this many nodes, it becomes 0 at infinity, and for the S functions, of course, it is non-zero, but after multiplication with r square, at r equals 0, it also, the radial distribution function, P, it becomes 0. So what do we see here for the radial distribution function? There are points at which P becomes maximum. Here is one point. There is a maximum here for P. Here is another point. At this point, there is another maximum. All right? And finally, there is a third point at which there is a maximum. Now, there is a concept of the most probable distance. I will call it RMP. This is the distance at which P, radial distribution function, has the highest value. Distance at which P has highest value. Of course, the mathematical condition for finding the most probable distance is the same as the condition for finding maxima and minima. In this case, maxima. So, mathematical condition is this. If we use this equation, this is the condition for finding maximum and minimum, all right? For this expression, this is the radial distribution function. How many solutions are we going to obtain? You see from the graph how many maxima are there? There are. How many? There are 3. This says the most probable distance is the distance at which P has the highest value. If you look at this graph, here is a maximum, here is another maximum, here is a third maximum. Which one of these have the highest value? From this graph, you see it is the outermost. So, this point is the most probable distance of the electron from the nucleus. So, the mathematical, arithmetical procedure is use the condition for maximum, minimum, take the derivative explicitly with respect to r, set it equal to 0, and then find r values. Those r values are going to correspond to maxima in the graph. Among these r values, you should select the one that will give the highest value for P. Okay. Before dealing with the 3p and 3d orbitals, please note, as a general rule, this maximum, location of this maximum, R value, is larger than this one, which is larger than that one. In other words, we can describe the most probable distance by saying that it is the outermost maximum. Outermost maximum. Outer means larger R value. You see, here we are talking about electron, and there is a positively charged nucleus. As R gets larger, the electron gets away from the nucleus. So we say outermost, outside of the nucleus, outside of the vicinity of the nucleus, larger, outermost. This is generally valid. When you find more than one maximum for the solution of this equation, the R value, which is at the outermost position, is the most probable distance. So, let us consider now 3p. R 3p. Here 3 minus 1 equals 1 node. So this function, as a function of R, has one node. Where is it? Between 0 and infinity. So here is let us say, that's a node, which means the function will cross the R axis. This is not a s orbital, or this is not the radial function of s orbital. It's a p-type radial function. So it becomes 0 at origin and also at infinity. Because all of these functions become 0 at r equals infinity. Then, we know the function is 0 at origin, this function, 3p. It has one node here, and it also becomes 0 at infinity. So, let us imagine the function value is increasing from 0 as r gets larger. But because it has to become 0 at this point, what is necessary for the curve? The curve has to descend. So now it becomes, it takes negative values for such r values after the node. Then we know that it has to become 0 at infinity. So how should this curve continue? It should go like that, isn't it? So this is the graph of this 3p radial function as a function of r. Now, using this graph, we may plot the p. We are squaring it, squaring each point here. The squares of the positive values are also positive, but squares of negative values are positive numbers. We are multiplying with this r square, but r square doesn't change the position of this point or that 0 or the 0 at infinity. So the graph is going to look like this is P, 3P. This is R, 3P. Now let us discuss the most probable distance. There are two maximum here, two maxima. One is this point, and the second is that point. So when we solve this equation for r, how many answers are we going to obtain for the 3p radial function? We are going to obtain two answers. One is this value, the second is that value. Then, according to this rule, outermost maximum is RMP. What do we conclude? We conclude that this maximum, this is RMP, the most probable distance of the electron to the nucleus. Let us, as a final example, consider the 3D radial factor. This time, 3 minus 2 minus 1 is 0. That means this radial factor, R3D, has no node. Remember, when we count the number of nodes, we are not including into the counting r equals 0 and r equals infinity, only in between. So between 0 and infinity, there are no nodes for this function. Of course, we know that all radial functions become 0 at infinity, and all these radial functions other than S functions are also 0 at origin. So 0 goes to 0. So what is the shape of it? Shape of the curve? Very simply this. This is qualitative graph of R3D. Now, the radial distribution function is R squared times square of this function. Now, because the function is already 0, itself is 0, squaring it doesn't change qualitatively anything. Also, multiplication with R squared doesn't change the behavior at origin qualitatively. So the graph of this function looks similar to qualitatively similar to this function, say like that. This is P. So how many maxima has this function? From the graph you see, only one, isn't it? So if you use explicit definition and use this condition for the P3D, you are going to obtain how many answers? Just one answer. And that R value is going to be automatically the most probable distance. About the value for the most probable distance, you see that these three examples have the same n value, principal quantum number. One is 3s, the other is 3p, the third one is 3d. In this case, the relative values of the numbers for the 3s radial distribution function, 3s, 3p, and 3d. What is changing? L value is changing. Here is L is 2. Here is L is 1. Here is L is 0. And same. This calculation shows that most probable distance, RMP, is largest for L equals 0. Then comes L equals 1. Then comes L equals 2. Is that understood? So there is a trend according to L value. As L, let us say it in the opposite way, as L increases, RMP gets smaller, closer to the nucleus. L is largest here. This value for this value is smaller than this value, and this value is smaller than that value. And this is generally valid. As L, same n, same principal quantum number. But as L increases, RMP decreases, gets nearer to the nucleus. Okay. Now, let us do these things mathematically, using this condition. I need some space. Well, let us use this part. We may use this equation by substituting the explicit expression for the radial function and then take the derivative, all right? And then put it equal to 0. There is an equivalent way, an alternative way of doing the same arithmetic. We may symbolically work with this expression and substitute here. Like this is r squared times capital R squared. The derivative of such a factor is derivative of the first factor times the second plus the first factor times derivative of the second. So let us do that. Derivative of the first factor times r squared plus r squared times derivative of this. But that is 2 times r times derivative with respect to r, isn't it? This is equal to 0. So now I can simplify a little bit. There is a capital R factor here and a capital R factor there, isn't it? So let us simplify. Also simplify here. There is a 2. Simplified because right side is 0. Also simplify this. What remains is r plus r times Is this clear? So, what this means is that when we are given explicit expression for r, for this r, you may either substitute directly into this equation and make this explicit, then take its first derivative with respect to r, put it equal to 0, and continue. All right? This is equivalent to another procedure. What is the other procedure? You take the explicit expression r and substitute here. And then take the derivative of r with respect to r variable, and then use this equation and find the positions of the maxima. You will obtain the same answers. It doesn't matter which way you proceed. Okay? So, I will do one example from R 3D. A normalization constant times r square times e to the minus r over 3. This is, now, in applying this equation or this equation, numerical value of normalization constant n is unimportant because n will cancel. The right side is 0. All right? So, this means put for r square e to the minus r over 3, just this part, because this, if you include n here, but n will also occur in the second factor, and then the right side is 0. Therefore, a numerical value of n is unimportant for this calculation. So what I did is I dropped the normalization constant from the beginning. I have taken just the r-dependent part. Now, if you take the derivative of this with respect to r, there are two factors. Derivative of this times that, 2 times r, plus this times derivative of that, which is minus 1 over 3 r squared times e to the minus r over 3. This is the result of this equation. So, all factors contain exponential. Exponentials, so the factors of the exponentials so let us simplify. R goes. Here is minus 1 over 3. Here is plus 1. 1 minus 1 over 3 is 2 over 3, isn't it? 2 over 3. I made a mistake someplace. Let us find out which one. This is R. How did I understand this? Because I will obtain a negative value for r here. On the other hand, we know that r is the radial variable. R must be between 0 and infinite. Where is the problem? This is correct. First derivative is 2r. Yes, this is derivative of the exponential is minus 1 over 3. We are multiplying with r square. That is also correct. But there is a problem. We are doing it for 3D. As we should obtain a positive value for RMP. Let us see where the problem is. Yes, I have forgotten to multiply with this r. This part I'm multiplying. So this becomes r square. This becomes r cube. Is that understood? All right. So now let us simplify. R squares can simplify. This is r square. This becomes just r. So what happens? 1 plus 2 is 3 minus 1 over 3 r. This is the factor of, this is e times e to the minus r over 3. And this has to be equal to 0. Because the exponential never becomes 0 between 0 and infinity, this factor must be 0. So that means r value has to be, what is it? 9. So this value here, what was our unit of distance? Bore radius. So 9 means 9 times bore radius, A0. If you are interested in the SI value for the most probable distance in P3D. I have repeated this calculation, and you can also do it, because the explicit expression for R3S and R3P are given to you in the notes. And you may also look up from physical chemistry textbooks. All of them contain such explicit expressions for the radial functions. And you may do this calculation. For 3p, we find that this value is 12. And this value is 3. Okay? So if you compare radial distribution function for the 3p radial function with 3D, you see that RMP is 12 in P3P, but it is 9 for 3D. In other words, as I said before, the most probable distance of the 3D is nearer to the nucleus than the 3p radial function, radial distribution function. This is generally true. If you repeat it for, compare 4s, 4p, 4d, 4f, or radial functions, and do this calculation for the most probable distance, which of these orbitals do you expect to have most probable distance nearest to the nucleus. One is S, the other is P, third one is D, fourth one is F. All of them have 4. Principal quantum number is equal to 4. We are comparing these orbitals. The F orbital, 4F, will have the smallest RMP value. That's what we are saying. Fine. Now let us, thus far we have discussed properties related to the radial function. Remember, our complete function a radial function multiplied with angular function. These are the spherical harmonics functions. Thus far, we discussed properties related with the radial function. Either directly graphs of radial function or the concept radial distribution function, P, which is related to the radial function. Now we are going to discuss properties related to the angular part. The angular part is this, the spherical harmonics. These functions are functions of 2 angles. One is theta, the other is phi angle. They have the following form. There is a factor which depends only on theta, the first variable, and it is indexed by the L quantum number and also M quantum number. But notice here I have placed M quantum number within 2 bars. It has a standard meaning. What does it mean? Absolute value. That means because M values can be either positive numbers or negative numbers, absolute value means you are going to use only the positive values for M. The second factor is this factor, in fact, the normalized function, 1 over square root of 2 pi times e to the I m times phi. The t factors, which depends on theta, are real. They are real functions, which means the actual expressions for t do not contain any complex number. Everything is real in them. For example, all are real valued functions. Don't bother about these factors. Those factors, like square root of 6 over 2, they are normalization factors. Okay? But when you look at the angle dependence, these functions are all real valued functions. On the other hand, the phi dependent part, this function, if m is 0, then 0 times I times phi will also become 0. E to the 0 is 1. Therefore, only when m is equal to 0, this factor will be real. Otherwise, it will be a complex function. Only for m equals 0, then this function will be simply 1 over square root of 2 pi. It is real. For all other m values, this factor is complex valued. Because of that, even though the first factor is real, but if this factor is complex, the full function is complex valued. So, we can say, summarize this. Y, L, 0. M is 0. L can have any value, 0, 1, 2, 3, 4, 5, etc. From this expression, we see that these functions are all what kind of functions? Real or complex valued? Real valued, isn't it? Because m equals 0 means m 0 here. Then it will become just a real number there. Are real valued for all L. On the other hand, for m not equal to 0, a non-zero value for m, y Lm are complex valued. All right, let us continue after the break.